Hi, my name is Cody Catrier, and I'm going to be giving a quick introduction and overview of Mordor, an open source library that we've developed here at Mosey. And just give you a quick overview here. There's a couple other deep dive videos if you want to get into some more details. And so let's just get started with what is it? So Mordor is a high-performance, event-based I/O library. It has some concepts from projects such as Boost ASIO, libevent, stack threads. So it's kind of that finite state machine or callback-based programming, but way different way of actually using it. So it can also be used as a parallel tasks library, similar to Apple's Grand Central Dispatch or Intel's thread building blocks, being able to easily dispatch a bunch of small tasks to a thread pool running on different CPUs. And it accomplishes both of these using fibers, which are lightweight threads. We'll get into details of what those are and show you a bit of how Mordor uses them. So it's implemented in C++, but it seems like a high-level language. We use exceptions, there's using a lot of Boost and some of those libraries, so it's very simple to program in, even though it is C++. And finally, it's cross-platform without compromise. And what we mean by that is that, usually when you do cross-platform, it becomes the least common denominator. But we don't want that. We want to use the best of each platform. So instead of choosing the least common denominator, we specialize pieces for different platforms so that they'll work the best they can, and we don't hide the native functionality. If you need to get at the native functionality for a specific platform, it's still there for you. So what can it be used for? One major use is network servers, which is what the non-blocking event libraries are traditionally targeted for. We're using fibers. It's very, very scalable, up to thousands of connections. Mordor has built-in HTTP client and server libraries. Very easy to write ones for other protocols and be able to handle thousands of connections at once if that's what you need to do. It can also be used for some client apps where Mosey is using Mordor and some of its own software to be able to push a lot of data up the pipe to our backup servers. You can use it even if you just want some of the ease of use of it, even if you're not going to use any, you don't really care about the high performance nature of it. You just want to use it because it's quick and easy to do it. And yet it can still easily work in your existing C++ code base. That's fine. The other thing is for parallelizing computations. If you want a cross-platform way to spread work across multiple cores, Mordor can be great for that. You could be using it just for some of the other features for coroutines or generators that you see in Python. These can be implemented in C++ with the fiber engine that it has. So how is it different from some of the other things out there? And you can write a network server that uses one thread per connection. That's the old naive way to do it, and it was very easy to see that threads don't scale. When you have 1,000 connections, 90% of your CPU time will be taken up just switching between the different threads handling those connections. So that was solved by using non-blocking APIs, using state machines and callbacks. But the problem with those is they're difficult for a programmer to write and understand what's going on. They're inconvenient to use, not what they're used to, and they're very difficult to debug. If something goes wrong, it crashes your stack trace, it goes back to the main event loop. It doesn't show how you got to where you are at that point in time when it crashed. So the answer is fibers. Fibers are somewhat related to threads, and their benefit is they appear synchronous. It's the programming blocking model that you're used to, but under the hood they're non-blocking. Instead of blocking, they have a non-blocking callback-based event manager underneath. So that gives them super high performance, but the ease of blocking programming. So how do they compare against threads? Well, fibers are kind of like threads, except they're cooperative. It's cooperative multi-threading. So before the days of preemptive multi-threading and multi-users machines, threads were cooperative. You had to explicitly relinquish control of the thread to allow another thread to run. And that's what fibers do. It avoids the overhead of context switches. You don't have to have the kernel do it and manage who's next. You don't get interrupted. And instead of blocking something, a fiber can yield to another fiber to allow it to run instead of blocking. So that from the operating system's perspective, we're keeping this thread very, very busy. But you need to remember that threads still exist. We don't need to go to a single thread and all the fibers like some other libraries that have explored fibers or event mechanisms work. They limit you to a single thread, but we still need threads. You have to have threads in order to utilize multiple CPU cores. And sometimes you have calls that are going to block. There's nothing you can do about it. On POSIX systems, the disk access is going to block no matter what you do. So instead of forgetting about threads or blocking your thread that you don't want to block because it's processing all your network requests, you can move that to a thread pool that you are allowed to block on that thread. And it's very, very easy to migrate a fiber from executing on one thread to another thread. It's just a single function call. You don't have to call anything else. There's no state machine, no callback involved. You just call switch to thread, and it works. Makes it very easy. So let's get into some examples here. We're going to show you how fibers work together with threads and then throw an exception in there for you. So we'll start out in main and we print out which thread we're on. And on the right hand side here you see the actual output, and we see on thread C40 here. Then we declare a worker pool that represents this thread, and then another worker pool with another thread. We get inside our try block and we switch to the other pool and output which thread we're on. And in the output we see we're now on thread 180. And we're going to then call throw exception, which uses Mordor throw exception. Now I've made it a separate function and the macro Mordor throw exception here to illustrate the stack trace that you get in Mordor. That when I use this macro, it attaches the stack trace to it, it throws the exception. When scheduler switcher goes out of scope at the end of the try block before the catch block, then it returns back to our original thread, and then it adds the next portion of the stack trace. And then we do a output which thread we're on again. In the output you can see that we're back to the original thread, C40. And then we output the exception diagnostic information from boost. And we're leveraging boost here. And you can see in the output that we have the stack trace for throw exception and main with actual line numbers. So that works on all platforms. With GCC, on some platforms you have to give us extra option to get it to have the symbols in there. This one was from Windows, but shows just how simple it is to use exceptions, to switch threads around, and all that. Our next example is parallelizing work. So it's kind of not as concrete of an example. We're just going to start a worker pool with 8 threads. We'll create a vector of some job that we need to do. And we're going to call parallel for each, passing it iterators to begin and end, and a function that parallel for each will pass each object in that vector. So work on job will do something hard, but it will be doing up to 8 of those at a time using 8 different threads. Once all of those jobs have completed, parallel for each will return. Our last example is a simple echo server, so doing network stuff. We declare our I/O manager, we create our socket, we bind, we listen, then we accept a connection. Now for each connection that we accept, we schedule on the I/O manager the function to handle it. And instead of creating, it looks like we're creating a new thread, but we're really creating a new fiber. So they all run in the same thread. Transfer stream reads everything from that socket and writes it right back out to it. And that all happening in the same thread can handle multiple connections at a time. And that was very easy to write. We're at, 20 lines there to create an entire echo server that can handle thousands of connections at a time. So that was just a quick sampling of what Mordor can do and how it might be useful for you. We have some other videos out there of deep dives into fibers, what they are, how they work, how to leverage them, and streams dealing with lots of data, and then how the HTTP server and client libraries work and how cool they are. So thank you for your time.